Okay, so this is JRFCQAI Arduino UNO Q based drone. On this, at the bottom part, there is Arduino UNO Q with STM32U5 and Qualcomm Dragonwing CPU. This is MPU 6050 6-axis IMU. This box is carrying MS5611 barometric pressure sensor. This is a GPS module which also having inbuilt HMC 5883 magnetometer, and this is 824C 32 kilobyte EEPROM to hold the parameters. Now, barometer, EEPROM, magnetometer, and IMU is connected to quick connector of UNO Q, and it utilizes a wire of the STM32U5. GPS module serial port is connected to Arduino UNO Q serial 3 at 115200 baud rate. This is FlySky FSI6AB receiver configured with iBus protocol, and it is connected to serial 1 UART1 of STM32U5 microcontroller. The objective of this flight controller is to provide AI capable drone platform as an open source experimental purpose. With Arduino UNO Q, this is a USB camera attached directly without any USB hub. The camera is getting power supply of 5 volt from buck converter of 5 milliampere 5 volt attached to lithium polymer battery. UNO Q is getting power directly from 3 cell LiPo battery, and the same is having a filter capacitor of 100 microfarad to filter out the glitch generated by heavy current flowing through motors. There are two resistors to provide voltage divider network of 1K and 10K for battery voltage measurement. The firmware of STM32U5 for flight stabilization is ported from Juke Brookings YMFC32 autonomous drone project, which is open source. Currently, STM32U5 and Dragonwing CPU is communicating via serial bridge on LPUART0, and I am using bridge notify calls to communicate between a Dragonwing processor and STM32U5. Here is a Arduino AppLab. In AppLab, this is a project work as a ground station as well as it incorporate AI brick. Current AI brick is video object detection, and current AI model I am using is YOLO X Nano. This Python code is providing ground station web page that can be accessed from any device in a same network. Here there is a GPS current location of the drone. Here is the telemetry data, and these are the buttons that can be used to control the drone. Here currently I am at the university premises, and the Wi-Fi network is having a many channel utilized, so there are some glitch in a Wi-Fi streaming. Now let's see the demonstration of the drone. These are 3 LEDs which provide the status feedback of the drone. LED blink once means current status is mode 1 auto level mode. If I switch to mode 2, it blink twice, that is altitude hold mode. And if there is a third position on this switch, then it is a GPS hold mode. Currently the weather is cloudy and not enough satellites available, so GPS hold mode may be not possible. So let's start with a auto level mode. Now I am making the drone arm. So as you can see, the drone is quite stable. And current flight mode is auto level. Because there is a limitation to provide only one unedited video, it is quite complicated to show the GCS at the same time. I request someone to hold the laptop. Laptop, ले लो. Now let me try to switch to mode 2. Okay, so this is the altitude hold mode, and drone is precisely controlling its altitude. As you can see, the weather is cloudy and currently only 5 or 6 satellite is possible to acquire, and the nearby trees are there. So I am skipping GPS hold mode. I'm asking now to બાજુમાં લેપટોપમાં દેખાય. So as you can see, the live status data of drone available on a ground station hosted by Dragonwing CPU. આડો હોડો થાય. Now I am once again switching to auto level mode, and let's land this one. ચાલુ જ રાખ. So current status of the drone, it is capable for auto level mode, GPS hold mode, altitude hold mode. The firmware includes wayport flying, as well as AI bricks can be used for autonomous missions. Now, the project is strictly for experimental purpose. It is open source, no license required. It is completely free. Even no attribution required to use this project for educational purpose. Current setup uses very standard sensors for sensor fusion algorithm. It's no way near to the Pixoc and other commercial flight controller. Users are advised to follow the airspace restriction rules while testing this drone. There is no guarantee or no warranty provided with the flight controller code and hardware. Currently, all the data is available on GitHub, and in the description of this video, you will find all the required links for code and hardware. The project is currently not fully completed, and it will take long to get it to the very precise autonomous flight control, autonomous drone. The future scope of this drone is consider hexacopter configuration and fixed wing airplane configuration, as well as use some more precise IMU as well as barometer, lidar sensor, time of flight sensor, and more precise GPS. I going to dedicated this project to Juke Broking, and all credit Juke Broking Reserve for his open source project YMFC32. YMFC32 project provide me a solid base to write the firmware from the scratch for STM32U5. I haven't used Pixoc or other open source LibrePilot like firmware because they are using different real-time operating system, while Juke Broking YMFC project is kind of bare metal programming that can be easily ported to the Zephyr OS running on STM32U5. Another thing, there are few challenges I have faced, and I have gone through the solutions. First challenge is I don't want to use bulky USB hub with power delivery. So I used 5-volt power supply directly to the camera, while the data lines are only connected to UNO Q USB Type-C port. For that, I need to fire some command in the SSH from UNO Q to enable the host mode, because after power up, host mode is not available. Currently, I am using GPS module which provides GMRS format data, which is more than 64 bytes. For Arduino API of STM32U5 in Arduino UNO Q, the receive buffer size is only 64 byte and there is no API available to change the receive buffer size. I tweaked underlying Zephyr OS to increase this RX buffer size from 64 byte to 512 byte. In a current API of Arduino UNO Q, PWM frequency for analog write function is fixed, which is 500 Hz. And to run this BLDC motors, I need a frequency less than 400 Hz. So again, I tweak underlying Zephyr OS to configure the frequency from 500 Hz to 355 Hz. Flight controller loop right now is running at 250 Hz, means in 1 second there are 250 cycles for sensor reading and PID control. To achieve this tight timing, I have used Zephyr OS functions like yield and kwait ms in a Arduino sketch itself. So the timing requirement, critical timing requirement is met. So thank you very much for your support and seeing this video. The project, as I told, the project is ongoing and you will find more videos on my YouTube channel. Thank you.